Hi, I'm Josh Benabou, and I'd like to tell you about our paper, String Theory and Grand Unification Suggest a Sub-Microelectronvolt QCD Axion. This is work with my excellent collaborators at Berkeley, Katherine, Fraser, and Ben Safdi, and at the University of Oxford, Mario Reig Lopez. In our paper, we concern ourselves with the QCD axion, a hypothetical particle proposed to solve the strong CP problem of QCD, which may also be the dark matter of our universe. We are interested in particular in extra-dimensional UV completions for the axion, which are interesting because they naturally address the so-called Peche-Quinn quality problem for the axion that plagues field theory UV completions of the axion. In our work, we address the question of whether there's any handle on the mass of the QCD axion for these extra-dimensional QCD axions, and we find the answer is yes, if we suppose that in the UV, the standard model unifies into a grand unified theory, a GUT, as in the MSSM. In this case, we establish a bound on the mass of the QCD axion, which is firstly an upper bound of roughly 10 to the minus 8 electron volts, and a lower bound of roughly 10 to the minus 11 electron volts. This bound is independent of the fraction of dark matter made up by the QCD axion. This bound is interesting, firstly, because it is totally disjoint from the mass range expected for the post-inflationary QCD axion dark matter, which is a scenario that most naturally arises for field theory axion UV completions. And secondly, because it is targeted by next generation direct detection experiments, such as dark matter radio GUT and CASPEr. The basic logic underlying our upper bound on the QCD axion mass is as follows. Suppose that the standard model gauge couplings unify at the SUSY GUT scale, roughly 2 times 10 to the 16 GeV, as in the MSSM. Then Kaluza-Klein resonances of these standard model gauge bosons, if they have masses which are below the GUT scale, then the picture of MSSM-like gauge coupling unification is generically altered by threshold corrections. So we must impose that the mass of these Kaluza-Klein resonances must be at least mGUT. In a number of extra-dimensional examples that I will list shortly, we have verified that the QCD axion decay constant is never parametrically below this KK scale. As a result, the QCD axion decay constant is never parametrically below the GUT scale. The examples which we have examined in our work for which this bound holds true include a 5D orbifold GUTs, for example, with a flats or a warped extra-dimensional geometry, heterotic string theory, axions from higher p-form fields, where the decay constant can be computed analytically, assuming an isotropic manifold or a Swiss cheese manifold. And in addition, a numerical scan with a sample of roughly 2 million type 2b compactifications on Calabi-Yau threefolds in the so-called Kreuzer Skarke axiverse. For example, in the Kreuzer Skarke axiverse, we find that the QCD axion decay constant scales inversely with the square roots of the volume of the 6 extra dimensions which are compactified. The requirement that the KK scale, which is decreasing as the volume increases, be above the GUT scale imposes an upper bound on this 6-dimensional volume, and as a result, a lower bound on the QCD axion decay constant. As a corollary, we find that in the Kreuzer-Skarke axiverse compactifications with more than roughly 50 axions are incompatible with field theoretic unification into a GUT. A key step in our logic underlying our upper bound is that the QCD axion decay constant is not parametrically below the KK scale in these examples that we have examined. In our paper, we present an argument based on unitarity for why we expect this relation between scales to hold more generally across the string landscape. The argument is as follows. So consider the scattering 2 to 2 of gluons mediated by an axion. The amplitude for this process grows with energy as the Mandelstam variable S over Fa squared, and is constrained by partial wave unitarity. It is bounded above by an order 1 constant. The 4D axion EFT should be unitary up to the KK scale, which implies a lower bound on Fa of, parametrically, the KK scale. In our work, we also discuss caveats to our bound. These include theories with pseudo-anomalous U1s, where the QCD axion can arise from the mixing between a higher form field and the phase of a complex scalar field. In such scenarios, the QCD axion decay constant can be pushed parametrically below the string scale. An additional caveat is to accept that the KK scale be below the gut scale, as can occur, for example, with large volumes or from warping. But then the model builder is challenged to evade proton decay bounds, with proton decay occurring from operators like the one shown here. Lastly, as an additional application of our methodology, we search for axions in the Kreuzer-Skarke axiverse, which can explain the recent DESI evidence for evolving dark energy. We find no axions with high enough decay constants. That means larger than roughly 2.5 times 10 to the 17 GeV. And as a result, we disfavor the axion interpretation of the DESI evidence for evolving dark energy. Thank you for listening, and we hope that you'll check out the paper.